VLSos here. This is a video lesson on area under the curve estimates from data. Typically we use mathematics and science works with data, often collected from an experiment. If we're fortunate, science could arrive at understanding a situation in the real world and create a model, or an equation, which then we could use as a tool of prediction. But our ability to estimate accurately and the tools in the mathematics for estimation is often more practical because we're often not working with a model, we're working with an incomplete model or a data set. So let's imagine that this set of data came from an experiment and we want to find the area under the curve, so to speak, of just this information, an incomplete set. Well, it would be helpful to visualize the information that we have. I'm going to graph this data set with vertical intervals of 2. The highest value, vertical value in the set of data is 15. I'll make a tick mark there. And if we go by ones on the horizontal axis, we get to 12. 12 is our, no, we need to get to 15. I'm going to make a scatter plot of this data. 0, 5, 3, 10, 6, 11, 9, 15 is our highest point, 12, 13, and 15, 6. So with an incomplete model, these data points, to ask what is under the curve of these data points, would suggest that there is some curve that might connect all of these data points. We just don't have the equation for it. So what do? With incomplete, or an incomplete function, we have to estimate, and we have a few different techniques. We can use left rectangles, right rectangles, and trapezoids, as well as a handful of other techniques, but we're going to focus on presenting these three. So what do we mean by left rectangles? If all we have is the function values at these locations, then those function values at those locations are going to serve to be the heights of a set of rectangles. We're going to have 5 rectangles, and if there are lefts, it means that the height of the rectangle that I make under the curve is going to be based on the left end of the rectangle, or the left side. If I draw lines to represent the heights at each of these known data points, then I don't use the last one because it would be outside the bounds of my information. I could draw then the sides of the rectangles to complete them, and the set of rectangles that I've drawn here would be an estimate of the area under the curve. And I can calculate those lefts from the table of data. I can see that every rectangle has a base or a change in x of 3. That's helpful. Not necessary, but if the base of every rectangle is the same, then it helps organize the calculation. This first left rectangle, its area is the base of 3 times the height of 6. The height of 5. And the height of 5 is information in the table. So if I multiplied 3 by 5, I'd get the area of this first one. The area of the second is going to be the base of 3 multiplied by the height, which is the second point, a value of the point in the table. Every single rectangle is going to be 3 times a value that's in the table, except for the last one, because I do not make a left rectangle from the last data point. There's a pattern. I'm going to multiply 3 by these first 5 values to produce the areas of the rectangles and then add them up to be the estimate. I can make that an efficient calculation if I first add the first 5 data points in the table and then outside show that I'm multiplying each one by 3. This expression then is a very efficient way of calculating the estimate using left rectangles. I can do that with right rectangles. Right rectangles would be rectangles whose function values was representing the height of the rectangle on the right side. So if I draw boulder lines, 2 points on my scatter plot, then I can show these heights to be what we call the right rectangles. This first right rectangle, its area is that same base of 3 times the function value on the right side, which is the second point in the table. Notice that if I'm going to use right rectangles, then I skip or do not use the first function value. All right rectangles are going to be 3 times a value in the table. The last 5 values make the 5 right rectangles. That's an efficient expression if I draw the change in x of 3 outside of a parentheses, and inside I add up all of the heights. This expression is for the right rectangle estimate for the area under the curve. These two estimates, I've done the calculation, have exact values of 162 for the left and 165 for the right. So I know that the exact area is in between the estimate that is lower and the estimate that is higher. We use a capital A to represent the exact area. We don't know what that exact area is, but we do know that the exact area is in between 162 and 165. We can get more accurate approximation of the exact area using trapezoids. That means that instead of a rectangle as estimating the area under the curve, if we attach 2 adjacent points with a line, then we create a new top of a shape, but the shape is no longer a rectangle. This shape here is a trapezoid. We often view trapezoids where the lowest side or the side that's on the bottom is one of the parallel sides of the trapezoid. But this is a trapezoid, even though it's standing, we could think of it as standing upright. It has 2 parallel sides and 2 other sides that don't need to be parallel. The area of a trapezoid is the average of those 2 parallel sides, we call them the bases, times the height. The height of every trapezoid that could be made from these points is 3. And the bases are the function values, sequential function values. So the expression to calculate and add up all of the trapezoids is again the height of 3 times the average of the bases. Well, the bases are going to be the bases of the first trapezoid are going to be the first two function values, and we add them together, 5 and 10. But to average them, after I add them together, I have to divide by 2 or multiply by 1/2. I can show multiplying by 1/2 outside, because every time I take an average of the two bases to create the area of a trapezoid, I will be multiplying by 1/2 to take that average. I can show that multiplication by 1/2 outside the parentheses because it will distribute to every trapezoid that I'm going to find and add together. So this next trapezoid, its area is the sum of its bases, which is 10 and 11, divided by 2, which is why we have the multiplication by 1/2 here, and then times its height of 3, which we also already have ready to go. So to complete this expression, what I need to do is simply continue to add the two sides of every trapezoid. And notice that the inside data in the table, each one that's on the inside is going to be used twice in that sum. And the ends, 5 and 6, are only used once to complete the expression for the trapezoid estimate of the area under the curve, which I've previously calculated to be 163.5. Notice that the trapezoid estimate is in between the range that we previously knew. This trapezoid estimate is a better estimate than 162 and 165. So why wouldn't we use the trapezoid method every single time if it's going to be more accurate? We can see that it's going to be more accurate because if, and we don't know, if this dotted line represented the actual function, then the left-sided triangle is an underestimate by this region. And the the left-sided rectangle is an underestimate by this region. The right-sided rectangle is an overestimate by this region here. And the trapezoid method is an underestimate by this sliver of a region. So the trapezoid method has less error. Why wouldn't we use the trapezoid method every single time? Because we don't know if this estimate is over or under. If the function was here, we could observe that it's under, but we don't have the function to actually determine whether this 163.5 is over or under the actual error. So the rectangle method to get a range also has its use because the exact area is known to be definitely in between.